So in this set of videos, I will introduce a new application that we have in MDA tools, which is called DD-SIMCA-LOVE, which is also implementation of a new method recently published in Analytica Chimica Acta. So let me start the application. So just go to mda.tools, open any browser, any modern browser, go to mda.tools, and then click on this DD-SIMCA-LOVE. So this is the main application window. And here in the bottom, you can see two links. First of all, it's a link to the paper describing the method. The paper is open source, so I recommend you to read this paper first. So it's available for everyone for free. And then also link to data sets that I'm going to use in this video, so you can also download and follow my examples. So I will just unzip the data and then show you what is inside. So you can see that inside we have 3 files. It's a very famous wine data set about 3 Italian wines. Every wine is characterized by 27 variables. And then you can see I have 3 subsets. It's a training set, it's the test set where I have the same samples as the training set, the same class as the training set, and then new. What is inside? So if I go to training set, for example, so let me just make it smaller. So you can see that training set consists of wine samples belonging to Barolo class, Barolo type, where we have the name of the samples, the class name, and then the variables. You can see 27 numeric variables of different nature. Then in the test set, we have also Barolo class samples, but fewer. So it's just the same class. And then finally in the new, we have some other types. As far as I remember, it's Grignolino and Barbera. Okay. So it means that I can use the compliant approach to optimize my variable selection process, meaning I can take into account both the members and the strangers. So let's open the data. So first of all, we need to select the file with the training set. So I just load this file, and then as in any apps in MDA tools, it automatically recognizes the correct settings. So you can see the delimiter is comma, it has row labels, and it also has header, which is a variable names. And by default, it's mandatory. It also assumes that you have a class name, column with the class names. Okay, so I load this data. The next step is to build a global PCA model. Similar to DD-SIMCA, I just use enough number of components, much more than optimal. And then I also need to auto-scale this data in this case because all the variables have different scale and nature. So I create a PCA model. Now it's time to upload the target set. So it's a test set with the target class members. And there are 2 options. I can either generate it using PVSet, so Procrustes validation set. This option is also available in usual DD-SIMCA app. Or I can load it from file. And because I have now the target test set in the file, I will load it from file. So I click from file, and then now I have this possibility to select the test set. Okay. Again, automatically recognizes everything. So I simply click load, and then you can see this is the information about the test set. So now the next step is to load the alternative, the data set with alternative classes, members of alternative classes. And again, we have 2 options here. We can skip and then use rigorous approach, which will be based only on sensitivity, or we can load it from file and use the compliant approach, and this is what I'm going to do. Okay, so I select the new. So now everything is done, and the next step is to select the alpha, the expected type 1 error, the expected number of false negatives, and also the number of intervals. By default, it can work in 2 modes, either interval mode, where you have several variables in one interval, for example, or it can work with a variable mode. So it means that one variable is one interval. Okay. Because in this case, it's not spectroscopic data, the interval mode would make no sense to use, so I will use the variable mode. So it means that every single variable is a single feature or a single interval. Okay. So I have 27, it's the number of variables and the number of intervals. Before I run, let's look at this one. So here you will see the progress, and what you see now, it's a global model. By default, you can see if you use one component in the global model, meaning all variables together, that's the sensitivity we have, this is the specificity we have, efficiency and selectivity. And then you can see here, you can switch between 2 types of plots, intervals and statistics. If you click to statistics, you can see actually the plots with, in this case, it's sensitivity versus number of components, specificity versus number of components, and efficiency versus number of components. And there is also selectivity, secondary statistics that can help you in selection process, which we are going to talk about a bit later. Okay. So in this case, you can see that, for example, if I use 6 components, I can use selectivity. I can increase actually the selectivity, right? So now we're ready for selection process. So I click run. And then you can see that this little yellow rectangle shows which model is calculated. The idea is following. It takes this variable out. For example, let me select it, right? It takes this variable out, calculate a model without this variable, and then put it back, take this out, calculate model without this variable, put it back, and so on and so forth. So the process is similar to IPLS, the interval PLS selection. Okay. So now what you see here, it's the statistics, different statistics. In this case, it's efficiency, you can see. Which efficiency we will get if we, for example, remove the alcohol from the variables. You can see that we will have a drop in efficiency, right? So we will have 970 instead of 987, which is the global model, right? And then you can see this is for one component, right? So you can actually change the number of components for 2 components, for 3 components, and so on and so forth. So you can see what will you get if you remove any variable here. You can also look at the statistics. So the blue, it's the current best model, which is a global model. And the red, it's the model without variable that I selected. It's a variable number 1, alcohol. Okay. So if I go back to intervals, I can also see that, for example, in this case, I will increase the efficiency. In this case, I will increase the efficiency. In this case, I will increase the efficiency, and so on. However, if I increase the efficiency, what happens to specificity and sensitivity? Right? So you can see that in this case, sensitivity will be equal to 1, which is not very good, actually, because the expected sensitivity is 0.95, and specificity will be a little bit higher than the global model. Okay. So how to select the proper variable for first exclusion? Well, the best way to do it is to look at this plot in the difference mode. In the difference mode, you see the difference between the previous best model, in our case it's a global model, and the current one for all 4 statistics, for all 4 figures of merit. Then you can see, for example, this one. You can see 4 columns. The first one, the first bar, it's the sensitivity. Then we have specificity, efficiency, and the selectivity. And if you select it here, you can see the corresponding bar is highlighted with a darker color. So in this case, you can see that, for example, if I remove this variable, or this one, or this one, or this one, or this one, I will get the increase in the efficiency, right? So which one to select? Well, I will select, surprisingly, this one. Why? Because it actually doesn't change the sensitivity, and the sensitivity will correspond to the 0.95, which is expected. It is okay to increase sensitivity, but at the very end. At the beginning, it's a good idea to keep the sensitivity close to what is expected. Okay. So let me remove chloride, and before removing it, I'll show you what happens if I remove it. So you can see this is what happens to efficiency, right? So you can see for the first 3 components, it will be pretty high, and then it will drop here. This is what happens to specificity. This is what happens to sensitivity. And this is what happens to selectivity. You can see selectivity will get a little bit higher. Okay. So let me go back and remove it. So now it's removed. Now this is a new best model. You can see without interval number 14, without variable number 14, 2 components. And this is the comparison. You can see same sensitivity as global model. Specificity is higher, efficiency is higher, and the selectivity is higher. Now we have 1 out, 26 in, and it's time to make a new run. So let's make a new run. All right, so now apparently the best candidate, so let me select efficiency again, which increases efficiency without actually changing the sensitivity, it's this one, right? So again, I can look at the statistics. You can see this is what happens with efficiency, a bit higher than the previous model. Specificity, sensitivity is more or less the same. This is selectivity is a bit higher. Apparently it's a good candidate, so let's exclude it. Run it again. So you can see this is the progress. Now this is the best model. Again, if you compare it, for example, specificity now is equal to 1. We already have a pretty good one. And now because we already have almost ideal model, we have expected sensitivity, we have ideal specificity, what we can do, we can simply continue and try not to make it worse. Or alternatively, we can also try to improve the selectivity. For example, in this case, apparently if I remove variable number 15, total phenols, the selectivity will be a little bit higher, right? Let me see the statistics. Let me make sure that it will not change the efficiency or the specificity, right? So you can see sensitivity is okay. Here we have a little drop, but for the first two components, it will be the same. Specificity is a bit higher. You can see here, right, in this area. This is efficiency. This is selectivity, a bit higher. So let me remove it. And again, you can see the update here. Now we can make a new run. So what is next? So next you can see that there are no intervals which, for example, improve any statistics. But for example, interval number 6, you can see it has a little drop in just 0.1% drop in the selectivity, right? You can also see it here. And then you can check the statistics again. You can see that this is how selectivity looks like. Efficiency, more or less the same. Specificity is the same. Sensitivity, more or less the same, right? So I think it's safe to remove it. So once again, the basic idea is not to improve the model at this stage, but not to make it worse, right? And apparently, if we remove variable number 6, we will not make it worse. So I exclude this one. Then you can see 4 out, 23 in. And by the way, if you, for example, don't like your decision, if you excluded the variable and then found out that it's not the correct choice, you can always go back. For example, you can see I go back and now 6 is back, right? So let me just remove it again. You can go back and forth and, for example, undo some of the not very nice decisions, right? So let me exclude it, run it again. So again, you can see what's going on here with the process. So next probably it's 20. Again, you can see that it doesn't change anything. It makes a little bit increase, a very small increase. Probably it's just noise in selectivity, but it doesn't make the other statistic worse. Again, I can look at the statistics. You can see this, the red is the model without this variable. The blue, it's a previous best model. And then you can see, again, doesn't make it worse. Specificity, good. Efficiency, selectivity, all the good. Excluding, okay. Now, what else you can do? You can also look at the progress, what has been done so far. You can see this is what's going on with your, for example, in this case, it's a selectivity step by step. So this is the global model after first variable, excluding the first variable, the second, the third, and so on. So we have 5 variables excluded so far. Then you can make a zoom in, and then you can see, for example, okay, selectivity increased from 0.97 to 0.9 something 997, right? Almost 1. And then you can also see this is efficiency, this is specificity. You can see from 0.975 to 1, and this is sensitivity. It remains unchanged, right? Okay, so now let me continue the selection process until it's over. I will make it very fast. I will just increase the speed of the video. There is nothing specifically important in this process. And then when I reach the end, I will get back to you and explain what you can do more. All right, so we're almost done. So you can see that there is only one variable is left, which is actually does not change the model. And look at these numbers, right? So we got ideal numbers just by excluding these variables one by one, carefully selecting the variables for exclusion. And then we can exclude the last one, run the last process, and then you can see there is nothing that can be excluded without actually making the model quality worse. Okay. So this is our selection. You can see 7 variables, only 7 variables are left, and then we got perfect classification results. The most important things are here. So first of all, you can download the file with outcomes, and which includes the full progress and the model. So let me download the both and then show you what is inside. You can see that the progress file just simply shows all these steps that you can also see in this table in form of CSV files. You can see the excluded interval, number of PCs at this time of exclusion, what was going on with sensitivity, what was going on with specificity, efficiency, and selectivity. And the model is actually the normal SIMCA model, which you can use in DD-SIMCA app. But this model already knows which variables to exclude. So it means that you can apply directly to a new data set without actually excluding these variables manually. Okay. If you like, you can also download the results because this model was already applied. For example, this is the results for the alternative set. Again, if you look at the results, you can see this looks exactly like the normal DD-SIMCA app if you used DD-SIMCA app before. So you can see some statistics here, and then you can see the information about every sample in the alternative. And these results are for the last step, for this one, right? You can also download the reduced data. You can see the training, the target, and the alt. So let me download the training set, the reduced training set. Again, if you look at the reduced training set, you can see there is only 1, 2, 3, 4, 5, 6, 6 variables is left. Of course, it's 6 variables is left here, not 7. So this is the reduced data set, which you can also use, for example, to train your SIMCA model and then to test it using the reduced target set and alternative set. Okay. If you go to MDA Tools again and click on DD-SIMCA app and load the normal DD-SIMCA app, you can actually go, for example, to predict new, upload this model that we just created, this one, upload it, and now you can load the original data without excluded variables, for example, this one, and it will be automatically, you can see it automatically produces the results, automatically excluded all the variables, so you don't need to actually take care of this. Now look how good the classification is. You can see all these samples are indeed outside the acceptance limits. Let me just make it to logarithm scale. Now let me download this plot. And now I'm going to do the following. I'm going to train this model using full data, all 27 variables. Train it, scale, across this validation, 2 components. So this is my model with 2 components. With 3 components, I can change the number of components later. Now I go to predict, and then I load this new model that I just created with all variables together. I select the same new dataset, the alternative classes, and look how different their predictions are. So this is what I get if I use all variables in the dataset, and this is actually what I get if I use only the reduced numbers, the 7 numbers that we reduced. You can see how big the difference is, right? So they are more dense, but they also are more far away from the decision boundary in general, right? So it has like a more dense cluster, which is located outside the acceptance area. Okay. So this is actually it. I hope you will enjoy the new method.